Hi, welcome back. So we are in Chapter 3 HCC VO1 project at the outline workflow of the project. In the previous session, we have explored the essential step in our application to execute the workflow, and that is to design the AI model. I hope now the idea of this AI model and this graph in front of your screen it's quite clear to you how we actually put all the pieces together. What we want to do now, we would like to go and execute this into code language using Python. I have created a number of sections here where each section contains number of cells accordingly. First, with the essential libraries. Usually I like to put all the libraries I am interested in, the essential one on the first, and you run them. Sometimes you might see me also calling them back again. So as usually you run these this cell, and all the libraries that we need will be important for this session. Now, as I have mentioned earlier before, that the use of different Python version, it doesn't go good with Keras pre-processing or TensorFlow in general. According to TensorFlow documentation, that the TensorFlow library supports Python version 3.9 to 3.11. So that's why I would just wanted to make sure in this session to run on Python 3.11. The important part starts actually from viewing the dataset. We have seen previously that our dataset will be within the train, and I just call the path, reach out to actually my drive and just copy the path of the two folders, both of them on the train. So the first folder will be for normal, and the second folder will be for the cases of pneumonia. Also, there is another folder for test purpose, but I just wanted to show you and explore the dimensionality of one picture and what the dataset looks like as an image. Basically, I wanted to loop over and pick up the path of the picture usually, and just store them all in two different variables. Call the image library from the PCL, and then use the open function to actually open the first picture in the normal class. Convert that into an array if I like to show you what that array would look like in a while. Let's check how many actually pictures are there in the normal and in the pneumonia cases, and also the shape of the image, which gonna represent the pixel or the dimension. And also we're gonna explore the image itself. So if we run this cell, what we will end up with the following. This is the image, which is something that we have seen before, and this image actually I've just graphed from the normal class, and the number of images in both in the normal number of images are 1,341 image, and also for the pneumonia is 1,341. So we have equivalent number of images to avoid any misleading of classification later on. This is a dimension or one image dimension, which is it's in here, we just graphed. It's 1,600 plus pixel by 1,900 plus pixel, so it's a quite a bit large image. We're not going to work on that much big picture. We're gonna resize that to be 200 by 200. So I could do that by, as I said, creating another function just to process the images before we feed them, or I can just use the built-in library with TensorFlow. Now, just get you to see this is an option if you like to actually save all the images as an MP array, just as creating the photo and the labels, so where each one of them represent as the name is indicating. A simple function that loop over the path that you have passed to this function, you basically get to determine the class or the output of that function. Depends on, so if it is, for example, happens to be the normal or happens to be the pneumonia cases. And then what you do, you open the image using the load image function, convert that into an array, and then append to a list which you have actually created in the very beginning here as returned. You will see in a while. And finally, to the label also you append the output. That's it, nothing special. And here I am passing both normal and pneumonia paths with the output either 0 or 1. And here are the photos that will be actually returned as an array, and here are the labels that's going to be returned as an array. Basically, after you finish, so you might use the save function using the MPY. This is a complete option if you like to utilize this dataset in a future work. However, I'm gonna keep working with an image format anyway. It's not gonna be dealing with MP format array. Now, here's the model train and test stage. So what are the steps? First of all, call again, just make sure the paths are there. The library, just to remind you one more time, the most important things to recognize that we need sequential, we need the conv2d, max pooling, the dense, the flatten, and of course the SGD, which I'm going to just walk you through in a while. Finally, the image data generator. The first function here we call defining the model. This basically is going literally to make work on this side of our graph. Let's translate that to code. So the first thing we want to do actually, it is to create a model by calling the sequential library. Now, the model is going to be sequential. And from here, we start to add tens or layers, as you might call them. The call that you are seeing in front of you, it depends on the documentation of Keras. You have got the conv2d, which actually going to take an input of the following. First of all, 32, 3 by 3. As we said that in every layer, we're gonna be feeding in the original input and then expose that to a certain filter. This filter could be inside 3 by 3, 2 by 2, 4 by 4, whatever you like. So this piece of code, say 3 by 3 is the size of the filter, or it's called the kernel. And what is 32? It is the number of filters. We have 32 of these 3 by 3 layers. And at the end, that each layer of these will be actually stacked on top of each other. Now, the activation will be using the relo activation, as we have discussed in many different occasions before. Padding, the original input will be padded or not. And the last things, maybe the last important piece here is to check the input shape. So we're going to be looking for 200 by 200. After you do that, we need to do max pooling, as we said. That is by taking the outcome of this, take the largest value. So in this max pooling, after every tens we create a max pooling by calling max pooling 2D function and say, well, max pool 2 by 2. This is the size of the kernel of max pooling. Now there is an output of this tens, and then you take it as an input to the second one. The second one is exactly the same, but this time I'm creating 64 filter of 3 by 3 and the same exact thing because the shape has been decided. Now the outcome of this, we cannot re-put it again in the second tens. And again, max pooling 2 by 2. And the third, it will be again 3 by 3, but this time 128 filter. After you finish, we're going to flatten the outcome. In the essential design, I said, well, I could create this like a 5 in your, and the second one is another 5 in your. Alternative to that, I just like maybe recommended structure to create 128. Finally, after you do, you create another variable to carry the function of SGD, which actually the propagation part, where you're gonna decide on the learning rate and something called the momentum. Actually, there are a number of them, not only the SGD, there is also the atom, and I think 2 more or 3. The technique will be different about taking the derivative of the propagation part. Finally, you call the compile function on the model that you have designed, and the compile function expects you to pass the optimizer. The lose function is going to be cross entropy, and finally the matrix of accuracy will be also executed. And that's it, you return the model. This is the function of defining the model. Of course, now you're going to call on this model So we create an instance of that function, the module, and basically we're going to now use the image generator. Now this image data generator, basically what it does, it take the original data set, which is the image, and rescale that into a value between 0 and 255. You can use also horizontal flip, and that is something related to augmentation of the picture. So take one picture and augment it on 4 different directions. Same thing you do for the test data set. So we have 2 image data generator now, they are ready to be executed. Now go to a variable defined as a train and another one called test. So what they are basically, the train and the test. The first one is by taking the train generator data engine we created up there, and then we call the function flow from dictionary function. Basically it takes a few variables. The first thing we want to take is where is the path of the training data set. In this case we call on the training directory that have 2 classes, and then we decide on the color mode, which is going to be 1 channel grayscale. If we don't, that will be considered the image as an RGB, so we have to be a bit careful in this case. The next thing we want to do is the class mode is binary, and of course we're going to be looking also the batch size of 64. Now 64, as we said, is the number of images going to be treated at once. And finally the target size, as we said, is going to be actually 200 by 200, as we actually explored earlier before. The same thing we're going to be working the second variable, and that is test at calling the test data engine again, which we have created with the image data generator. Call the function flow from dictionary and just make the exact same process we done before. So first we'll be looking at the path of the test, the color mode is a grayscale, and the binary, a class mode, and finally the batch size 64. And of course we're going to be confirming also the target size is going to be 200 by 200 to resize the image during the test. So basically the mechanism here is going to be by calling the module.fit. Module.fit expect what is the train, what is the test. That's the main one. So in the train here we say, well, this is the train which we prepared for you, and just make sure to look at the steps per epoch. So in every steps we're going to be depends on the length of the train. And the same thing for the validation variable here, we passing the test folder data set. Same we decide on the steps and the number of epoch, and of course the purpose just to show the progress. Last but not least, sometimes while you're running the model, if you run one time, then run it second time, you cannot always guarantee the same exact result. Sometimes the progress can be very good. So what you want is, you want, for example, to stop this once the module have reached, like say 92% or 93 or 95, something like that. Stop. So here we call the callback function. The callback basically it call in this form of a list some function. So I call it my calls here, and my call is an instance of a class called my threshold callback here with a threshold for 87%. I was okay, stop when it's 87%. And this is a class, actually I just override that class according to the recommendation. Okay, once you're done, go ahead and start by actually storing the module evaluation and graph that out. Now if you run this, the model now, or the session, will start actually looking at the progress and testing on the validity of the module. Now I'm not going to run that for now, I just wanted to show you can run on your own. But the point here, you can have alternative structure. This is one proposed structure. Another structure, for example, by looking at 32, actually it's almost identical to the previous one. The only difference here, if you look, is the density of 512 instead 120 is done before. This alternative structure, I use also a different compiler here. With using the ADAM instead of the SGD that I used earlier before. That is just remain the same. So you could use as many different structures you like, and then try to simulate around them and see what our differences are in there. After you do and you are satisfied with that, now it takes the time to outcome the module to save it. So the last step is if we agreed on one of those structure, for example, I am happy with the outcome of this structure, so I'm going to do the exact same thing. But the difference here now, I don't need the test dataset, so I'm just going to work with the train. That's why here I'm creating an image data generator only for the training folder. The training folder put on the exact same details as expected, and then what you do, you would like to save the module. So how to save the module? By, for example, calling on the H5 format. This is the point where you would like to actually save your model somewhere, and you will be using that later. In my drive, I have already saved 2 modules. For example, one is for the other project, this for a project. So the path here is H5. This is the module that will be used. When we spoke about the image or the technicality of a 3-step, is we needed this. This is the hccv01.h5. If we run this, the module then will be saved. Now we can move to the third and the last step is actually to work on the design of the GUI and the back end of our application, which gonna be actually mapping to the HCC V01. Basically, that's all what you have to know to execute actually the exact procedure. I'll leave the rest for you. You can call on the GPU, by the way, or you can execute on the CPU, it depends. And here is one more session just created for your information. If you would like to create completely independent function that is going to actually make resize of the image instead of using the keras. Now let's go ahead and carry on the progress to actually work on the GUI and the back end of our application. It's exactly what we're going to do next. I will see you then.